So our example now will be a beam with an internal hinge. And so we can take a look at the picture here. We've got a pin over here at A. We've got the internal hinge at B, and then a fixed wall connection over there on the right end of the beam. And this beam is going to be indeterminate. We're going to show the indeterminate is in the axial direction, and it's going to be determinate in the transverse direction. And we're asked to prove that the hinge does not move due to the loadings that are present. And then we're also going to find the slope at point A. So let's take a look at this beam from a determinate, indeterminate point of view. And so this is a complex structure. You have two pieces. We have AB and BC. So we're going to draw the whole structure free body diagram. So over on the left end, we have a pin, which is complete translational restraint. And over on the right end, we have complete fixity, both translation and rotation. So the free body diagram is going to have all the applied external loads. I've done components already for the 50 kip force, which is at a 3-4 angle. So we're going to have components 40 and 30. And I've got the two external support translational restraints on the left end, and on the right end the fixity is represented by two perpendicular forces and an unknown moment. So this free body diagram, the whole structure, has 5 external unknowns as we count them out in red. We only have 3 linearly independent equations, so this is externally indeterminate, so we're going to have to unhinge the beam. And so when we do that, we are going to take the beam apart right over there at B. That's going to result now in 2 free body diagrams. And looking at the free body diagram on the left, all right, I've decided to put the applied external load on the left side of the free body diagram here. So you see the 40 and the 30 exposed. Now are the internal hinge forces. I've called them F11 and F10. On the other side, we now have another free body diagram, and that's going to have the equal and opposite internal forces F10 and 11, and the wall forces. So now we've got a picture that has 7 total unknowns, the 5 externals and 2 internals, giving us 7. And we've got 6 equations of equilibrium, because we have 2 free body diagrams. So this is a 1-degree indeterminate problem. So why is it indeterminate in the axial direction? So as we look in the axial, we have 3 forces that have the exact same line of action. So we've got F2, we've got F10, and F3 that have the same line of action. So those 3 unknowns are going to only have 2 equations of equilibrium independent, 1 from each free body diagram. So it is indeterminate in the axial direction, and it is going to be determinate in the transverse direction. So what we're going to do is, using the free body diagram for AB, we're going to start solving for some of these external supports so that then we can find the internal moment. So if we look at the free body for AB, I'm going to go up, slide right back up here. So this is the one we're going to use. And it's a good starting point here because we have 4 unknowns. On the other one, we have 5 unknowns. So we want to start with the free body diagram that has the fewest. And so we're going to sum moments at the right end. And I'm going to then end up with a very nice solution for F1. And so that has solved now for the external support F1. We're going to now sum forces in the y direction on that same free body diagram. And doing that's going to give us an equation with F1 and F11 in it. We can plug in what we just found for F1, 40, and we would end up with a solution for F11. So what we've just done is, back in this free body diagram, all right, we've solved for F1 and for F11. And by doing F11 on 1, we've solved for the exact same force in the opposite direction on the other side of the free body diagram. So if we look now at the free body diagram for BC, this is exactly what it looks like. And so what we need to do is find the internal moment in that segment, and that's going to be able to assist us in finding the deflection at point B. So I'm going to use the blue saw, and I'm going to use the blue saw to expose m of x. This is only going to be valid for x from 5 to 15, just on the right side of the internal hinge. And so I'm going to end up with a cut, and that gives me now two free body diagrams. So I have one that's again cut at a distance x, and another one left over, which would be 10 minus x. And so I'm going to use the free body diagram on the left. And on the left, I'm going to quickly spin a moment at the cut. And when I spin a moment at the cut, I'm going to find out that m of x is equal to 0. So between points B and C, the moment inside the beam is equal to 0. So we're ready to get into our second order beam equation. What boundary conditions do we know? I know at the wall, I've got translational restraint, and I also have slope restraint. So I'm ready to do this. This just now becomes a little bit more mathy. I've got 0 is equal to the curvature. I'm going to integrate. We'll then use the boundary condition at 15, where we know the slope is equal to 0. That's going to give us that a is equal to 0. Integrate one more time. I now have that v of x is going to be equal to a constant. Using the boundary condition at v of 15 equals 0, I find that b is equal to 0. So this tells us that v of x is equal to 0 all the way from 5 to 15. Point B, the hinge, is at x equals 5. And so v of 5 is equal to 0. So we just proved that point B does not move in the transverse direction. So I'll put an up-down arrow. And now we're also asked to solve for the rotation at point A. So to do that, we're going to need to analyze segment AB, and we need m of x. We're going to use the blue saw again. We're going to cut that thing open, and we're going to find what's going on inside segment AB. So here's the free body diagram for AB as it sits. And we're just going to take out the blue saw and cut it. And so when I do that, we're going to end up with 2. So either side is going to have the, again, the same answers for the internal forces. And again, notice the sign convention on all the internal forces, and I've got equal and opposite here, such that when I put the beam back together, obviously all those forces cancel and become back on the inside of that beam. So I'm going to take the free body diagram on the left here. Again, this is without any loss of generality, and I'm just going to go ahead and sum moments at the cut. And by doing that, I should be able to solve for m of x. And so there's my equation, sum moments at the cut. Doing a little bit of math, there is my equation for the moment from 0 to 5 on our beam. What boundary conditions do we know? I know over at point A, I know that we've got translational restraint because of the pin, and I also know that we've got no movement at point B. So that's going to become our boundary conditions as we work through the math. So we will just slide right through this. Here's my moment equation over EI, right, is equal to the curvature. We're going to integrate. We get a constant of integration. I've got no boundary condition based on slope, so I'm going to integrate again, giving me an equation for transverse deflection. I'm going to apply my two displacement boundary conditions. I'm going to start with x equals 0, and plugging in x equals 0. Right, I get a 0 there, 0 there, 0 there. V of x is equal to 0, right, at x equals 0, so therefore C2 equals 0. So now here's the equation for transverse deflection. I'm going to apply the other boundary condition at x equals 5. So I'm just going to take anywhere I see an x, I'm going to plug in 5. Right? V at 5 is equal to 0. And I've just got a little bit of math to do. And I end up with an answer for C1. We're interested in the slope. So I'm just going to go right back to the slope equation that we had from earlier. Right there's C1. So all I've done is just plugged in C1 right there. And I'm interested in the slope at point A. And at point A, I know that x equals 0. So I'm just going to take this equation and I'm just going to plug in x equals 0. So that obviously simplifies quite a bit. Those go to 0. The slope at 0 then is equal to plus 333.3 kip feet squared over EI. Right, units police need to come out here because we've got E and I, which are in units of inches. And so I'm going to need to use a conversion feet to inches. And by doing the math, we end up with, again, the slope is going to be a unitless number. And so the math will come out to 0.0166 radians, and you could convert that into degrees by using pi radians is equal to 180 degrees. And so you'd end up with 0.95 degrees. And again, positive would be a positive slope. So the rotation at A is going to be up.